This is Professor Rogers. In this presentation, we look at the analysis of contingency tables, which are also known commonly as 2x2 tables.
Contingency tables are used when both variables are categorical. The most commonly used statistic to describe what is happening in the table is chi-square. Chi-square is used to test whether the data are distributed randomly in the cells of a contingency table. It determines whether variations from randomness are statistically significant, and thus is seen as a test of whether the variations are independent of the random distribution of points. Chi-square by itself is incomplete and needs to be supplemented. Gamma and Kendall's tau b give effect size and direction when both variables are ordinal or binary. Phi and Kramer's v give magnitude when at least one variable is nominal.
The example in this presentation has to do with whether education influences policy on the death penalty. The state is the unit of analysis. The hypothesis is that as the level and quality of education rise, the likelihood that a state will have the death penalty decreases. The frequency tables for these two variables are shown here. Our dependent variable is a binary variable on whether a state has the death penalty. The state is coded 1 if it has the death penalty and 0 if not. 32 states, 63%, have the death penalty. The education metric is an ordinal variable that combines educational levels and the quality of the education. Education has three categories: low, medium, and high. The modal category is medium. The crosstabs command produces a contingency table. It can be found using the path Analyze, Descriptive Statistics, Crosstabs. The SPSS command dialog box is shown here. The PSPP command box differs somewhat in the location of option buttons, but has many of the same capabilities as SPSS, so much so that we focus on SPSS exclusively in this presentation. The normal convention is to toggle the dependent variable into the rows box on top and the independent variable into the column box below it. However, the variables are frequently reversed when there are more values in the independent variable because of the way the output fits onto a page. Using the cells option, I select the observed or actual cell values and the column percents to be included in the table. The result is the output seen here. The totals at the ends of the columns and rows are known as the marginals. In a few moments, we will see that they play a special role in understanding the patterns in the table. In the lower right-hand corner, we have the grand total. The data comes from 50 states, which total 100% of the results. Each cell includes the number of observations in the cells and the column percent. Within each column, the percent totals 100%. For example, there are 9 states rated high on education, and they account for 100% of the high group. Only 2 of these states, or 22%, have the death penalty. We want the column percents. Here is the table without percents. It is hard to figure out if there is a relationship in the table, especially since the number of states at each level of education is so variable. However, if we eyeball the table with column percents included, we see a relationship right away. The likelihood that a state has the death penalty increases as the education level decreases. Only 22% of high education states have the death penalty. This percent rises to 67 among medium states and 86 among low education states. The chi-square statistic tells us whether non-random deviations in the table are statistically significant. With the crosstabs command is a statistics option, which allows us to select chi-square. Chi-square produces its own table of output, shown here. There are different versions of the chi-square statistic. While the results are similar for each statistic, I choose to examine further the results of the Pearson chi-square, because this statistic is the traditional chi-square statistic used in the analysis of contingency tables. Thus, we can say that the chi-square of the table is 9.766 with 2 degrees of freedom. The statistical significance of the result is given in the last column. 0.008 is less than 0.05, so we say that the result is statistically significant. We get one warning in this output. chi-square is inefficient when cell counts are below 5, and we received a warning message. The message is caused by high education states that allow the death penalty. There are only 2 of these states, so there is a possibility that this cell may distort the chi-square number. I will proceed in this presentation using the results as is, but in a real analysis I might change the table, perhaps recoding it to combine high and medium education states into the same education category. Here is the formula for the chi-square statistic. In the numerator, we take the difference of the observations in each cell from what we would expect if the distribution of data were random, and square it. The denominator is the expected value for each cell. The resulting chi-square number can range from 0 to infinity. The big issue is how to find the expected value. The computer does all the work for us, but we will work through this small example by hand so we understand it more. We start with the marginals of the table. Next, we calculated the expected value for each cell. Randomness in this case is not understood as having the same number of observations in each cell. Instead, we take the marginal as our benchmark. Whatever we put in the cells in aggregate has to result in the observed marginal. To do this, for each cell we multiply each row and column marginal together, and then divide by n. If you are really smart at probabilities, work through this calculation, and you will discover that what we are putting into the cell is a joint probability. Here the calculation for the expected value of each cell is shown. Now we have 2 tables to compare. The first table has the distribution of points in the cells as we actually observe them, and the second table has the expected value of observations calculated. Here the math is worked through by hand. This slide shows how the chi-square value of 9.766 is obtained. Like t, the critical value of chi-square varies by the degrees of freedom. However, instead of tying the degrees of freedom to the number of observations in total, we tie it to the number of cells. The formula for the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. Working through this calculation, we find that our degrees of freedom are 2. We now can say that we have a chi-square of 9.667 with 2 degrees of freedom. This information allows us to determine the statistical significance of the table. The shape of the chi-square distribution varies by the degrees of freedom. We want to find the critical threshold for determining significance. This determination can be done manually using a chi-square table. The critical threshold for chi-square at the 0.05 significance level is 5.991. If our chi-square value exceeds this threshold, we are statistically significant at the 0.05 level. Our example chi-square of 9.667 exceeds the value of 5.991, so we conclude that the finding that the likelihood of a state allowing the death penalty decreases as the education level increases is statistically significant.
Chi-square only gives us statistical significance for the overall fit of the model. It looks at whether or not the data are distributed randomly across the cells of the table. Other statistics are measures of association that give us effect size and direction. If both variables are ordinal or binary, we can calculate both remaining elements of inference using the statistic gamma or Kendall's tau b. If at least one variable is nominal, we no longer can have direction because nominal data is unordered, so direction makes no sense. However, we can still calculate effect size using gamma or Kendall's tau b. The crosstabs command dialog box has a statistic option allowing us to select the statistic that we want. The location of these measures of association are highlighted. The interpretation of these statistics is the same as Pearson's R. The threshold for a weak association is an absolute value of 0.1. The threshold for a moderate association is 0.3. The threshold for a strong association is 0.5.
Gamma is built on the logic of ties. Each cell is said to have ties to other cells. We look at each combination of pairs through the whole table. A tie is said to be positive if the second cell has a higher value on both variables than the first cell. A tie is said to be negative if the second cell has a lower value on the first variable and a higher value on the second. The formula for gamma is the ratio of the difference between positive and negative ties to the total number of ties. This statistic is standardized and takes on values between -1 and 1. If there are more positive ties than negative ties, the direction is positive. If there are more negative ties than positive ties, the direction is negative. Let P be the number of positive ties. Here all the positive ties are calculated. We start with the cell no for death penalty and high for education. Thinking of high as the low value seems strange, but behind the label high there is a value of 1. Medium has a value of 2, and low has a value of 3. No high is positively tied to yes medium and yes low, and no medium is tied to yes low. Let Q be the number of negative ties. We start with the cell yes high and work our way across again. Here the numbers for P and Q are plugged into the formula and we get a value of gamma that is approximately 0.69. Since this number is standardized, we conclude that we have a strong positive relationship between education and death penalty. This finding seems contrary to our theoretical hypothesis and what we saw eyeballing the table, but we need to recognize that the values for education are reversed, so the finding makes sense. Because of the way tables are displayed and the numbers calculated, we always need to review the results since the sign for direction is not intuitive. When we do that in this case, we realize that the relationship really is negative, as we hypothesized.
There's a whole debate over exactly which number should be in the denominator. In gamma, ties between cells on the same level are overlooked, but other statistics incorporate these ties. An example of one is Kendall's tau b. The result of increasing the ties is to lower the effect size. In addition, the interpretation falls from a strong relationship when using gamma to a moderate one in Kendall's tau b. We will discuss which statistic is preferable more in a moment. In the column on the far right is the statistical significance of both Kendall's tau b and gamma. We see that both are less than 0.05, so we conclude that the relationship is indeed statistically significant. The null hypothesis is that both tau b and gamma are 0, and we reject the null hypothesis based on this result. It is worth noting that some software packages, including PSPP, do not give us the statistical significance of gamma, so it is not fair to always expect to see it. If one of the variables is nominal, the effect size can be established using phi or Kramer's v. Each calculates the effect size using the chi-square. Phi is used when there is a 2x2 table. Kramer's v is used when the table is larger. Here we see all the measures of association we discussed together in this video. Note the similarity between Kendall's tau b and the phi and Kramer's v. Between the inability to calculate gamma in some software packages and the similarity with phi and Kramer's v, I find that Kendall's tau b is often preferable. In this presentation, we learned about the analysis of contingency tables, which are used when both variables are categorical. Chi-square is used to determine whether deviations from the random distribution of points in cells of a table are statistically significant. Gamma and Kendall's tau b give magnitude and direction when both variables are ordinal or binary. Phi and Kramer's v give effect sizes when at least one variable is nominal. In our example, we saw with gamma that the direction did not intuitively make sense until we recognized how the education variable was constructed. From this we learned that we should always visually inspect our tables when we use these statistics to make sure we understand what is happening.